All right, so today we're going to talk about absolute extrema, and let me write down the strategy to find them. So firstly, remember we're going to be using a closed interval, because for closed intervals, we're guaranteed that if the function is continuous, that the maxima and minima will be contained, or the numbers where this minima and maxima are obtained are going to be contained in the interval. So we're going to be able to determine them. So our first strategy is finding the critical numbers. Our step 2 is going to be to evaluate the function and you're going to evaluate it on the critical numbers and by the way, you're going to only evaluate it on the critical numbers that live within the interval that you're considering. There's no point on evaluating the function on the other critical numbers, so just use those. And you're also going to evaluate the function on the endpoints of the interval. Then number 3, you're going to determine which is going to be your absolute minima and your absolute maxima. So you're going to determine the extrema. Alright, so that is very easy. So let's take a look at one example as to how we can do this. Absolute extrema is perhaps the easiest topic whenever you're determining extrema. So this is a good one. So let's start with the function. It's going to be x to the 4th over 4. Then minus x over 2. Oh, that's a square. My bad. And then minus 12x plus 3. Or it was minus 3, but the number will change just slightly there. All right, so the step 1, find critical numbers. So this is a polynomial. So remember, critical numbers are those points where the derivative is going to be 0 or it's going to be undefined. But this is a polynomial. The derivative will be a polynomial. Therefore, we only look for where the points where the derivative becomes 0. So let's take the derivative and then we set it equal to 0. Because there won't be any points where the derivative is undefined. So 4 times divided by 4, you get x cubed. Here you drop the 2, cancel with the 2, you get minus 13x. And then minus 12. All right, that is correct. All right, so now we have a cubic function that we have to set equal to 0. All right, so how do you solve a cubic? Well, you could do Cardano's formula, but you don't have that. So what we can try is look at all the factors of negative 12 and of 1, and with those do combinations, so ratios, so we can find one that would possibly will work. But thankfully for this example, you can pick negative 1 here. This is going to give you negative 1. So at x equals negative 1, you get negative 1 cubed minus 13 times negative 1 minus 12 is equal to what? You get negative 1 minus negative, so plus 13 is plus 12 minus 12 is equal to 0. So just like that, we found a root of the polynomial. So perfect. So what do we know now is that since x equals to negative 1 is a root, we can then divide the polynomial by x plus 1 in order to find a quadratic polynomial that then we can solve with the quadratic formula. So this one turned out to be a little bit more exciting than I thought it would be, but it's okay. So we have then here an x squared that we multiply here, we get x cubed plus x squared, and we subtract it off. X cubed minus x cubed goes away, and I get negative x squared, and I drop my 13x. So now how many x's can I fit in x squared? Well, I need negative x, well, negative x squared, I suppose. So negative x, I get negative x squared minus x. So when I subtract it all off, I get negative x squared minus negative x squared is plus x squared, so cancels. And then negative 13 minus negative, so plus, you get negative 12x minus 12. And then you just have minus 12 here, which gives you 0. So what that is telling you is that our function f prime can be written as x plus 1 times x squared minus x minus 12. So now to find all possible critical numbers, I need to find the roots for this polynomial. So I'm going to factor, and I get x minus 4, x plus 3. They add up to negative 1. They multiply to negative 12. And I find that all my roots are going to be negative 1, 4, and negative 3. One thing I did not tell you, I gave you the function, but I did not give you an interval. So what is the interval we're going to be using? It's going to be negative 2 to 4. Of course, you could pick any, but let's see then which critical numbers live in the interval. And I chose this one so we could leave at least one out. For example, x equals negative 3 is not in here, but x equals to negative 1 is in here, and x equals to 4 happens to be an endpoint. So I got kind of the whole gamut of possibilities there. One on the end, one is an endpoint, one is inside of the interval, and the other one is outside. So our critical numbers then are going to be given by this, and then we're going to be able to evaluate it. So let me erase the computation, so I just record the information that we need, and then we'll keep working on the steps. All right, so now we copy the critical numbers there. Of course, there was a lot more work that happened, but now we can move on to step 2, which is evaluating the function on the critical numbers that live in the interval and the endpoint. So I need to evaluate f of negative 2, one endpoint. Then let's move on to the first critical number, f of negative 1. Then we have f of, well, negative 3 is outside. We don't care about that one. So the next one is f of 4, which is both a critical number and also an endpoint. So we evaluate the function there. Now, a common mistake is to evaluate the derivative. You're going to get 0. Well, at least for the critical numbers. And the endpoints, they're going to give you nothing. But a lot of people make that mistake. So evaluate your function here. So I'm going to go ahead and do that, and I'll come back with the numbers. Okay, so after putting this in the calculator, and please verify my numbers because I did it in my head, so maybe, maybe not. But the point is here, we're getting 3 different numbers. 35/4, which is going to be higher or larger than 5, is going to be my absolute maximum. Now, negative 85, which is smaller than 5 and 35/4, is going to be my absolute minimum. And so this right here was going to be my step 3, basically, is determining which one is the largest. That's going to be your absolute maximum, and the smallest is your absolute minimum. So it's pretty straightforward. Once you have your critical numbers and you plug them back into your function, all you have to do is find the largest number of all. That's going to be your absolute maximum. And the smallest is going to be your absolute minimum. So this problem was quite exciting. We had to find a root of a cubic, which is okay. And then we had to evaluate our function and then find our maximum and minima. Let's do one more. So firstly, we have to know what the domain is. The domain of this function is going to be all numbers that are going to be different to -1, which is where the denominator becomes 0. So our interval is contained in the domain, so I don't have any problem there. I just have to then find my critical numbers as my step 1. Find the derivative, so this is a quotient, so we do quotient rule. Derivative of the numerator, 2x, times the denominator, minus the derivative of the denominator, which is 1, times the numerator, which is x squared minus 2. All over the denominator squared. Now, when is the derivative undefined, even before we simplify? That's when the denominator happens to be 0, which would be at x equals to -1. -1 is outside of our interval. It's not even in the domain of the function. We don't have to care about that one. So all we have to care about is when this function becomes 0. So let's simplify it a little bit. Distribute the 2x, we get 2x squared plus 2x minus x squared minus negative plus 2 all over where we get x squared, 2x minus x squared, 2x squared minus x squared plus 2x plus 2, my bad, all over x plus 1 squared. So now you can look at this function and try to factor it when you set it equal to 0. Let's put my 0 here. Let's start the equation there. And you will not be able to factor it. So what is going to happen is you're going to end up doing a quadratic formula there. So 2x, I kicked something down there. Don't mind me. So negative b is going to be -2. Plus minus square root of b squared, so 4, minus 4ac, so 4 times 2, so 4 times 2, which is 8, all over 2a, all over 2. Now you notice here you get 4 minus 8 is -4 in the inside of the radical, and that's a problem because then we get complex solutions, which is going to be -1 plus minus I. Your solution, once you compute it, it doesn't matter. What matters is there's no critical numbers in my interval because they're complex numbers, so we don't care about them. We don't consider them for our analysis because we're only considering the function on the real line. So at this point then we have no critical numbers because the other possible critical number would have been when the denominator is 0. That gives us a point where the derivative is undefined. However, that value of -1 is not in the domain of the function, so we don't count it as a critical number. Next, when we do the first derivative test, we will use those points, but not at the moment. So step 2 would be to evaluate the function at the critical numbers or at the endpoint. So there's just no critical number, so evaluate it at the endpoints. I was going to write a 3 there. I do not know what happened. And when we evaluate here, we get 1 minus 2 is going to be -1 over 2, so -1/2. And then when we evaluate it at 3, we get 9 minus 2, 7 over 3 plus 1, 4. So this is the absolute minimum because it's the negative number there. And this is my absolute maximum. So this was an example where you don't have a critical number inside of the interval. For some reason that tends to cause trouble to students. people wonder, so what do I do now? Then there's nothing I can do. Yeah, you still have endpoints. You still have to evaluate those. And then the largest number will give you your absolute maximum, and the smallest will give you your absolute minimum. So that's basically all you have to do for absolute extrema. Here are your steps, and you just have to be careful with your computations, but the principle is simple. So let's go ahead and move on to relative extrema in the next video.